In this video, we're looking at integrating even powers using trigonometric identities. So if we have sine to the 2n of ax, or cosine to the 2n of ax, we can use our double angle identities to write them in terms of cosine of 2ax. And then if we have something like cosine to the 4, we just apply that multiple times. So let's take a look at it with this example 5 here. So rewriting it out, it's the same as cosine squared squared. So using this identity up here, cosine squared of 2x is going to be a half cosine squared of a half cosine of 4x plus a half. So we get then if we were to expand that using the square, we get a quarter cosine squared of 4x. We get a quarter plus a quarter, which gives us a half cosine of 4x. And then we get a half times a half, which is a quarter. All right, but we still have a square term here that we want to get rid of. So what we're going to do is apply the identity again. So we get a quarter of a half cosine of 8x plus a half, and then we still get what we had. What we can do now is expand and simplify, so we get 1/8 cosine 8x plus 1/8 plus 1/2 cosine 4x plus a quarter dx. So that then gives us, if we integrate it, 1/64 sine of 8x plus 1/8 sine of 4x plus 3x on 8 plus c. So we can see there that coefficient of 8 dropped out to our coefficient. That coefficient of 4 dropped out to our fractional coefficient. And then our 1/8 plus our quarter is 3/8, which then just becomes 3x on 8. Because it's a constant, so when we integrate it, it just adds the variable x. So if instead we're looking at a product of powers of sine and cosine, we can then use the fact that that product is equal to half sine of 2ax. So in our case here, we can rewrite sine squared of x on 2, cosine squared of x on 2 as the square of the product. So that is just going to be the square of a half sine of 2ax. Well, in our case here, a is a half, so this is just going to become a half sine of x all squared with respect to x. And so we just get here 2 sine squared of x dx. And then we can just use that identity that we found above. That's going to become 1 take cosine of 2x dx, which is just x, take a half of sine of 2x plus c. You might be wondering, why is this 1 and not a half? Well, that coefficient of 2 got distributed to both of them, so they don't have that coefficient of a half that we had up here. Okay. Next example, example 7. This is looking at integrating different powers of sine of cosine. So what if one of them has a power but the other one doesn't? So we're going to use substitution here, because sine is the derivative of cosine. Well, negative sine is the derivative of cosine, and cosine is the derivative of sine. So we'll get some cancellation with our dx term, just like we have in the previous videos. So for this, actually, I don't want to jump straight into my integral. I actually want to define my variable. So let u equal cosine of 3x. Then your derivative is equal to negative 3 sine of 3x. So if we make dx the subject, dx is going to be equal to du on negative 3 sine of 3x. And so we can see there this 3x is going to cancel with that 3x when we do our variable transformation. So substituting it in, we get sine of 3x, u to the 4, because it's cosine of 3x to the power of 4, du over negative 3 sine of 3x. So let's get out our orange cancelly color. That sine of 3x cancels out, and this is the same as u to the 4 on negative 3. Taking out that constant of integration, we get negative 1/3 integral of u to the 4 du. So that's just going to give us negative u to the 5 on 5 times 3 plus c, which is just negative cosine to the power of 5 of 3x over 15 plus c. Okay, if we have odd powers, we're going to, so this is a product of an odd power of sine and an even power of cosine. We're going to apply the Pythagorean identity. So sine of cubed 2x is equal to sine of 2x times sine squared of 2x. And we can replace that sine squared of 2x with 1 take cosine squared of 2x. Oh, sorry, that's not squared, that's just sine of 2x. 1 take cosine squared of 2x. So what we're going to do is substitute that in for our sine cubed, and what we find is we just get the integral of sine of 2x times cosine to the 4 of 2x, take cosine to the 6 of 2x with respect to x. So now we can just treat it like we did the previous example. So we let u equal cosine of 2x, because we know that then our du dx is going to be negative 2 sine of 2x, which means when we do our variable transformation for dx, we're going to get some cancellation of our sine of 2x term. Sorry, these should be flipped. So let's just place them, du on negative 2 sine of 2x. So now substituting in, we get the integral of sine of 2x times u to the 4, take u to the 6, du on negative 2 sine of 2x. We get our cancellation of the sine of 2x, and we're just left with negative 1/2 times the integral of u to the 4, take u to the 6, du. So all we're left with here is negative u to the 5 on 2 times 5, plus u to the 7 on 2 times 7, plus c, which gives us cosine to the 7 of 2x on 14, take cosine to the 5 of 2x on 10, and let's just neaten that up as well. And that is the answer to our integral. So we can see we started with something that was a little bit more confusing, and we made it simpler by cancelling out the sine term with our variable transformation. But before we could do that, we did need to use the Pythagorean identity to make it something a bit more familiar. Okay, we also have cases where we have different coefficients of our angles. So we have to transform them so that they have the same coefficient. So in our case here, we want to replace sine of 2x with something in terms of x rather than 2x. So sine of 2x is equal to 2 sine x cosine x. That's just our double angle formula. And so there are two ways that we can apply this. The first way, well, let's just have a look at this first way. So we get the integral of 2 cosine squared of x sine of x dx. We then want to let u equal cosine of x, just like we've been doing in the past. So we know dx is going to be du on negative sine x. This becomes negative 2 u squared du, which is just negative 2u cubed on 3 plus c, which of course is then just going to be negative 2 cosine cubed of x on 3 plus c. Okay, but there is a second method that we can do here using the product identity. So cosine x sine of 2x dx is the same as a half sine 3x plus 1/2 sine x dx. And so now, even though their angles have different coefficients, it's now a sum rather than a product. So we can split this into two separate integrals and just compute them individually. So we get negative 1/6 cosine 3x minus a half cosine x plus c. And you're probably thinking, hang on, that doesn't look like that. And you would be right, it doesn't look like that, but pop it into your graphics calculator or into Wolfram Alpha or any sort of graphing process program, and you'll see that those two functions are identical. So there's actually a identity that you can use to make them look the same. And we've got a note down here for that. Note, different methods appear to result with different answers, but can use trigonometric identities to verify solutions are identical and graphically. Solutions will differ by a constant, which is of course in our c term. So really these c's are not identical. We might have c1 and c2 that account for the differences between the two functions. Okay, I think this is our last example for today. Integrating powers of tan or cotan. So recall that the derivative of tan of x is secant squared of x, and the derivative of cotan of x is negative cosecant squared of x. We also have some identities, which is tan squared x plus 1 is equal to secant squared x, and cotan squared x plus 1 is equal to cosecant squared of x. So if we have this first equation, tan squared can be written as secant squared x minus 1. And why is that more useful to us? Well, we know the the integral of secant squared of x is just tan of x, and we know that the integral of 1 is just x. So this becomes tan x, take x plus c. So nice and neat solution to that one. B is going to require a little bit more work. In fact, I'm going to start it on the next page. So let's rewrite it. Okay, so what we want to do here is a variable transformation where we let u equal cotan of 3x. Now, why are we doing that? Well, we know that the derivative of cotan of x is equal to negative cosecant squared of x. So we know that our derivative here, when written in terms of dx, will have that cancellation that we're always looking for. So du dx here is equal to negative 3 cosecant squared 3x, which means dx is just du on that negative 3 cosecant squared of 3x. All right, so doing our substitution, our integral now looks like this. It's negative u squared times 3, but then we also get du on negative 3 cosecant squared of 3x, and then we also have a let's actually move this a bit to the right because I forgot our middle term of cosecant squared 3x. So we get some cancellation. We get that those two cancel out. We get that 3 cancels out. That shouldn't have been a negative. So what we're left with, really nice and neat, u squared du times -1. So negative u squared du, which is of course just negative u cubed on 3 plus c. So all this becomes is negative cotan cubed of 3x times a third plus c. So very complicated integrand actually just becomes a single term cotan cubed 3x times negative a third. So we can get really complicated integrands, and as long as we can find that derivative of u that cancels out with our product, we know that we're going to be just fine. And that's all for this video. Thank you very much for watching.